radio frequency circuits.
Okay, folks, we're going to slow this down just a little bit because radio frequency circuits is what we really want to understand as best as possible, or what I want to understand.
The frequency can be varied over a wide range, and that at any frequency, the voltage of the source always has the same value. And once again, we're back to our old friend Triangle Trig. Just this last piece. Furthermore, in inductive reactance, the voltage leads the current, while in capacitive reactance, the current leads the voltage. All these things must be taken into account when reactance and resistance are combined together in a circuit. This is probably going to sound really dumb, but I'm just assuming that what we're talking about here is in a inductance and reactance in the same circuit, taking care to size these properly so it's kind of a balanced circuit. The resistance absorbs the voltage, I think. The key is to have a balanced circuit so you get current flow, I guess. I don't know. At the frequency, the voltage drop across the coil equals the voltage drop across the condenser. Since the two drops are 180 degrees out of phase, 180 degrees out of phase, yoinks, yoinks. At that frequency, the amount of current flow is determined wholly by the resistance. Also, at that frequency, current has its largest possible value. Remember that we assume that voltage to be constant regardless of frequency. A series circuit in which inductive and capacitive reactance are equal is said to be resonant, or to be in resonance, in tune at that frequency, which the reactances, I guess, of both inductance and capacitance are equal. So if all that stuff is true, this is a balanced circuit, I guess.
Or a resonant circuit is more proper to say.
What this says, Scooby-Doo schwap-dwap, this is a resonant curve at the top, I guess. The smaller the resistance, the larger the resonant current. So I guess you can see that as the resistance is pretty high here, the current is pretty low. So the smaller the resistance, of course, you have maximum current at the top. That must be a resonant point right there, right?
How would I know?
Under the voltage rise topic, they talk about the Q factor. The ratio of reactive voltage to applied voltage is equal to the ratio of reactance to resistance. This ratio is the Q of the circuit. Therefore, the voltage across either coil or condenser is equal to Q times the voltage inserted in series with the circuit. I'm not sure if this is the same thing, but talking about Q, the Q multiplier, the Hammerlin receivers have them. The guy says, I never quite figure out what a Q multiplier does. There's a Heathkit model QF1Q multiplier on eBay. Got me wondering. I know the Q is regarding inductors, capacitors, reactive divided by resistance, but I don't know how the Q multiplier does or how it connects. I assume it connects to a receiver, but I'm not sure about that. Obviously, it multiplies the Q, but of what components and stages?
In brief, it's a circuit that improves the selectivity of a radio receiver. For narrow bandwidth signals like CW or Morse code, this can allow you to hear the one signal you're interested in and filter out others, or null out or suppress a signal nearby in frequency that's interfering with the station you want to listen to.
I do see transformers now, capacitors with cores on one side and a Q multiplier, but it's vacuum tubed, so guess what? I'm not sure this has anything to do with the Q in a circuit, but since it has vacuum tubes and it's old and it's Heathkit, I'm gonna be looking for one of these babies. So I think the gist of all of this stuff is to, like, here's a circuit, it's reactance because it's AC, alternating, current, like a signal and a sine wave. The whole point is to have current flow and be able to control it. I think maybe that's what the resistor is for. And I'm pretty sure, I'm just guessing, folks. I'm gonna go through this again off camera, but they're showing a resonance, I believe, up here with I think this is that circuit capacitance, and as they go along, this is cool too. They're kind of showing that this is the same thing. These two are the same. But as they go along here, let's see, different types of resonance, parallel resonance, and there was another graph in here. Yeah, it's the inductor coil that you can switch and change inductance on. But yeah, here is a this is a relative impedance of a parallel resonance. So these different circuits they're showing, and then they're showing how the Q changes, and the more Q as you go up, since Q is resonance, the higher the Q, you're up and you're resonant and there's current flow. This is current, yeah. So resistance goes down and the Q goes up. It's a lot to understand for me, and I think this is stuff that I'm going to go through again. I'm going to go through the whole thing, the whole chapter 2, with a fine-tooth comb and a notebook, and make serious notes after this, because I think this is really important. And since I have old equipment, my goal is to be able to work on this old vacuum tube gear that I have and understand what's going on. Yeah, it's 1950s, but this stuff is complex, man. No, there's no IC circuits or computer programming in this radio stuff, but I feel this is stuff that I can learn and be able to work on the radios, possibly buy some test equipment, and that can make the hobby more fun, I think. So yeah, there's a lot going on. We're going to keep going on here with LC constants, and it's going to get pretty intense here. So I think as far as inductive coupling, yeah, and let's see, we're just kind of cruise through this a bit here. Link coupling, selectivity. So they talked about selectivity. I think this is radio circuits. I'm pretty sure the Q relates to a Q multiplier. I'm just guessing though, but selectivity, that's a topic in receivers, and they're gonna explain what that means in circuitry. So what else we got here? Piezoelectric crystals. Yep, heard of those. Combine AC, DC. AC, DC, rock and roll. Anyway, so yeah, I'm just looking through these things. Series parallel feed. Some of the stuff I don't know what it is, but I think there's definitely enough stuff. Grounds, yes, you must ground your radio. Yeah, I'll go through a few more of these, but you know, there's a lot here that, yeah, vacuum tube principles. So before I even get to this chapter, I will go to it, but I think when we finish this, I'll do maybe a couple more videos on this chapter. But I think after that, probably gonna stop for a while and just analyze chapter 2 with a fine-tooth comb and try to take notes, because sometimes when I'm going through these things, I have to write down notes and kind of write it down in a way that it makes sense for me, because there's a lot going on here. They kind of write this and splash it all down on the paper in a pretty good order, but I kind of need to kind of reorder it somehow and taking notes so that it flows in a way that my brain can sort of comprehend what in the hell's going on. All right, well, thanks for watching, folks. It's getting quite intense, but this is enjoyable, and I hope you're getting something out of it. Just if you want to, just get the book yourself, go download it, and it's a slow process for me, you know, to comprehend these things and to learn them. I'm going to have to take notes and reorganize things and think about this stuff in my mind and how they all build together, because they do. Each concept, if I didn't get the one before it, I'm lost when I get to the next one. So have a good day, folks, from your old pal, CLG, Sid G.